Modern wide-body aircraft utilize three primary fuel storage areas, two within the wings, and one central fuselage tank. During the refueling phase, engineers prioritize filling the wing tanks before adding any propellant to the center section.
A network of nearly 80 sensors monitors the exact mass of fuel distributed throughout these massive storage cells. As lift pulls the wings upward, the massive weight of the fuselage exerts intense pressure on the wing roots. By keeping fuel in the wings longer, the downward weight acts as a counterbalance to aerodynamic lifting forces. Consequently, the fuel management system is programmed to deplete the center tank first to maintain structural wing relief. Once the central reservoir is exhausted, the engines begin drawing from the main wing tanks to finish the journey. However, a nearly empty center tank can harbor dangerous vapors, especially when heated by adjacent onboard electronic equipment. High-temperature air conditioning packs located beneath the tank can raise the internal temperature above the fuel's flash point. If an electrical short occurs in the aging sensor wiring, a spark can trigger a catastrophic vapor explosion. To eliminate this risk, modern jets use a nitrogen generation system to displace volatile oxygen with inert gases.
The process begins by diverting high-pressure bleed air from the engine's compressor stage into a specialized cooling unit.
A ram air intake opens to provide external cooling, bringing the superheated bleed air down to manageable temperatures. This cooled air enters a separator, where oxygen molecules are stripped away and vented outside the aircraft hull. The remaining nitrogen-enriched air is then pumped directly into the center fuel tank to create a safety blanket.
By keeping oxygen levels below 12%, the system ensures that combustion is impossible, even if sparks occur. This intake air is then compressed through multiple stages, drastically increasing its pressure and internal thermal energy.
In the combustion chamber, fuel is atomized and ignited, creating a high-pressure plasma that drives the engine. The force of the expanding gases spins the turbine blades, which are crafted from advanced heat-resistant superalloys.
As the air exits the rear nozzle, it generates the forward thrust required to propel the aircraft.
Modern high-bypass engines derive most of their power from the cold air flowing around the engine core. To survive extreme conditions, components are engineered with single crystal casting and specialized thermal barrier coatings. Onboard computers continuously analyze thousands of data points to ensure peak performance and early maintenance detection. Advancements in aerodynamics and materials continue to push the boundaries of fuel efficiency and environmental sustainability. Understanding the science behind flight ensures a safer and more efficient journey through the skies.
Modern jets utilize fly-by-wire technology, converting physical yoke movements into digital signals for the onboard computers.
These signals travel through fiber optic cables to high-pressure hydraulic actuators, located at the edge of each wing.
To initiate a roll, the ailerons deflect in opposite directions, creating asymmetrical lift across the aircraft's wingspan. Pitch is controlled by the elevators on the horizontal stabilizer, tilting the nose upward or downward during flight.
The rudder, located on the vertical tail fin, manages yaw, allowing the pilot to align the nose precisely. During takeoff and landing, trailing edge flaps and leading edge slats extend to increase the wing's surface area.
This configuration maximizes lift at lower speeds, ensuring a safe transition between the runway and the sky.
Multiple redundant systems ensure that control is maintained, even in the unlikely event of a primary power failure.
Precision engineering and digital logic work in harmony to keep the aircraft stable in every phase of flight. As the aircraft nears the runway, massive hydraulic cylinders swing the landing gear into the locked position.
Nitrogen-filled shock struts absorb the immense force of the landing, cushioning the transition to the ground. Multiple carbon ceramic brake discs compress against each other, generating intense friction to decelerate the heavy fuselage.
This kinetic energy is converted into extreme heat, requiring specialized ventilation systems to prevent component melting.
To prevent tire blowouts, an anti-skid system pulses the brake pressure thousands of times per second.
On the ground, the pilot uses a tiller to steer the nose wheel with mechanical precision.
The auto brake system maintains a constant deceleration rate, allowing the pilot to focus on runway alignment.
Once airborne, the gear retracts into the belly, sealed by streamlined doors to minimize aerodynamic drag.
From touchdown to takeoff, these robust systems ensure the aircraft remains stable on the terra firma.
Modern glass cockpits replace hundreds of mechanical gauges with a streamlined array of digital liquid crystal displays. These screens provide pilots with a high-fidelity representation of the aircraft's attitude, altitude, and vertical speed.
At the heart of the avionics suite is the flight management system, the primary computer for navigation. Satellite data and inertial reference units track the aircraft's position within centimeters across the global grid.
High-frequency radios and satellite links maintain a constant connection between the cockpit and air traffic control.
Pulse Doppler radar systems scan the horizon, detecting turbulence and moisture to guide the aircraft around storms.
Transponders communicate with nearby aircraft, providing automated warnings to prevent potential mid-air traffic conflicts.
The autopilot system executes complex flight paths with superhuman precision, optimizing fuel burn and passenger comfort. Hidden in the tail, the flight data recorder logs thousands of parameters, ensuring every flight is analyzed. The fusion of digital intelligence and human oversight makes commercial aviation the safest form of travel.
Cabin pressurization allows passengers to breathe comfortably while flying at altitudes where the air is too thin.
The fuselage acts as a high-pressure vessel, reinforced with titanium frames and carbon fiber skins to prevent expansion.
Outflow valves at the rear of the aircraft constantly modulate to maintain the ideal internal atmospheric pressure.
Fresh air is sourced from the engine compressors, then scrubbed through high-efficiency particulate filters for purity.
This superheated air passes through massive air cycle machines to be cooled to the exact temperature requested.
In the event of a sudden pressure loss, chemical oxygen generators provide an immediate supply of breathable air.
Advanced fire suppression systems use inert gases to extinguish flames in the cargo holds without damaging equipment.
Potable water and waste systems are integrated into the fuselage, managed by digital vacuum and filtration units. Insulation blankets and thermal shields protect the interior from the extreme cold of the stratosphere outside.
Every breath taken on board is the result of a complex dance of chemistry and mechanical engineering.
Aircraft structures must withstand millions of stress cycles throughout their lifespan without a single structural failure. Specialized testing facilities apply massive hydraulic loads to wings, simulating decades of flight in just months. The transition from aluminum to carbon fiber composites allows for lighter, stronger, and more fuel-efficient airframes. Artificial intelligence now monitors structural health in real time, predicting maintenance needs before they ever become critical. Looking forward, sustainable aviation fuels and hydrogen propulsion aim to eventually eliminate the industry's carbon footprint. Distributed electric propulsion and blended wing designs represent the next frontier of radical aerodynamic efficiency. Every nut, bolt, and line of code is a testament to over a century of aerospace evolution. Engineering excellence ensures that the sky remains a global highway for connection and human discovery.
From the ground up, we are redefining what it means to travel through the heavens.
Thank you for exploring the science of flight with us. Stay curious and keep looking up.